Hello guys, welcome to today's video on mensuration.
This is not a dream.
I like to pronounce it. So we're looking at shapes, figures, and looking at their properties. Let's start with the first one. This is a square. Why do we call this a square? This is because it has all the sides equal. Now, each pyramid is identical with the next. They are exactly the same pyramids. So we can use them as units for measurements. So we can have 3 units of pyramids here. You can see we have 3 here, 3 there, 3 there. Because you have the same number of sides of pyramids for each side of this shape, internal shape, we can call this internal shape a square. Now, it changes if we have another shape. When this moves around, we can have this moving around. Yes. And all of a sudden, this is no longer a square because the properties have changed. So you have 2 on this side and 3 on this side. The internal figure created is no longer a square. This is a rectangle. Yeah. Now, apart from that, what other shapes can we discover? So we can keep the side here, extend the side a bit, and then continue to create. Yes. So this here is another shape. What internal shape have we created here? This is a triangle. This internal shape is a triangle. You can see it has 3 sides. Yes, and specifically this is a right angle triangle because there is a 90-degree angle at this spot. There's a 90-degree angle here, which means that these 2 lines, a vertical line and a horizontal line, and the measured angle here is 90 degrees. What else can we look at? What other shapes can we look at? The next shape we look at is the rhombus. So you would notice that it was a square that was flipped to obtain the rhombus. So the rhombus has all the features of a square, as you can see here, only that it is not lying flat on its side. It's rather on the pointed side, and it looks more like a twisted square, except that all the lengths are the same in relation to a square. Another thing about the rhombus is that these diagonals, the line that you connect from end to end, they meet at 90 degrees at the center. The lines that connect from end to end meet at 90 degrees at the center. So take note of that. Our next shape is a kite. Now the kite is obtained by simply extending the side of a rhombus, like so. So as you can see, this has an extension on this side. So this is a kite, and it has 2 of the sides the same, 2 shorter sides and 2 longer sides, but facing different angles, angled in a sense. The interesting thing about a kite is that the area of a kite, you can easily calculate the area of a kite by using this length and this length to calculate it. If you watch carefully, if you split this into 4 parts, you get a square figure here, square figure here, square figure here, and a square, well, a 4-sided figure here, and a 4-sided figure here. So what happens is that you notice that it's half of that 4-sided, each 4-sided figure is inside the kite. So, and the area for that 4-sided figure that bounds these corners is this length times this length. So the kite will be half the area of this rectangle that covers it. So all you need to do is just measure this, measure that, multiply them, and you have your area of the kite. Another way is to draw a line here, find the area of half the kite, which is a triangle if you look at it, and then find the area of the other half of the kite, which is also another triangle. So there are 2 ways of finding the area of a kite. Next, we look at a parallelogram, and let's see what a parallelogram is, the tongue twisting. Parallelogram. So this figure is a parallelogram. Why? Because it has 1 pair of parallel sides and another pair of parallel sides. How many pairs of parallel sides do they have? They have 2 pairs of parallel sides. So this will mean that a square, which also has 1 pair of parallel sides and another pair of parallel sides, is also a parallelogram. And also a rhombus, which is a twisted square, a flipped square, will also be a parallelogram because it will have 2 pairs of parallel sides. A rectangle is also a parallelogram. It has 2 pairs of parallel sides. So as long as you can shift this to get 2 pairs of parallel sides, that figure that you're looking at will be a parallelogram. But note that a kite is not a parallelogram. It doesn't have pairs of parallel sides, right? Yes, it doesn't have 2 pairs of parallel sides, so we will not essentially qualify it as a parallelogram. Now the next shape that we are going to look at, which is also not a parallelogram, is the trapezium. So the trapezium, my bad. So unlike a parallelogram, this is a trapezium, and a trapezium has only 1 pair of parallel sides. This side is parallel to this side, but this side is not parallel to this side, so only 1 pair parallel sides makes a trapezium. So no matter how the shape is, as long as it has only one pair, it could be cut here, it could even be turned upside down. As long as it has only one pair of parallel lines, you define it as a trapezium. This is our next shape, which is a circle. Well, at least let's imagine that this is a circle. As the number of pyramids expands, it gets finer and finer to the shape of a circle. Of course, the line that you draw from one end of the circle to the other end of the circle, going through the middle, we'll define that as the diameter. We'll define this as the diameter. So this is the diameter of the circle. Of course, half of the diameter that runs through the circle, half the diameter, will be given a special name, radius. So this is the radius of this circle. Of course, this is the circumference, the measured distance around the circle. And what else can we mention about the circle? Yes. Now we can also look at, so when you have two radius drawn to the circumference like this, the area that is created here is called a sector. This is the sector. This is the arc, and these are the two radius. So a sector is made up of an arc and two radius meeting at the center. Of course, if you cut this circle at any point, just like you would cut an orange, let me flip this on the other side. If you cut this, yes, so this top part is a segment. So the segment also has a chord. This is what you call the chord. The line that cuts through the circle is the chord, and then the arc that's created. So when a chord and an arc meet, they create a segment. So notice it's just one line and an arc. A sector had two lines with the arc that go through the center. Notice that. So we've looked at the radius, looked at the sector earlier. We've now seen the segment, and we've seen the chord. Go the center, and then the distance from one end through the center is the diameter, as we saw earlier. So now we perform an experiment to discover how to find the area of this figure. So let's imagine that the circle that we have, let's picture this as our circle. Of course, this is a hexagon, but it's going to help us to understand what we're doing here. So let's picture this as our circle. And being a circle, we are going to split the circle in two, right? Yes, or we can split the circle on this side, similar to opening up an orange. Now when you do that, you notice that you create a zigzagged figure. So when you open up a circle, cut the end of a circle through the radius of a circle to the center and spread it out, what you'll get is this jagged edged line. Now what we can do now is, notice that because it's a circle, we can split it in two. After splitting it in two, we are going to transpose this jagged edge onto this jagged edge. I hope you can see what we're doing. In other words, a circle has created a parallelogram. What was a parallelogram? Parallelogram is a plane figure with two pairs of parallel lines. So the circle has been transformed into a parallelogram. So we can go further into a specific type of parallelogram. So let's see what parallelogram we can create out of this. So remember that we cut the circle through the side, we cut the circle through the radius, right? And then we spread it apart. Now what happens after this, getting this parallelogram, what happens if I slice this piece here, right? And then what do? Get this piece. So this, we sliced this here and connected it on this side. Now what this means is that a circle, we can get out of a circle a rectangular shape. Notice that the distance from here to here marks the radius. We cut through the radius. So, and we have this here being half the circumference. By lifting it and fusing it here, we fuse the other half of the circumference here. So this is half the distance around the circle. This is also half the distance around the circle. When I flip it back, it all comes together. Meanwhile, remember this as the radius, this as half the circumference, and this as half the circumference. As you can see, what we have just discovered is that a circle can be transformed into a rectangle. And when we cut through the radius and spread it out, we are going to get a jagged edged figure. And if we split this jagged edge, remember, so the whole circumference is what lies flat. Now we cut that and then transpose it into itself. We're going to get a figure like this, which is sort of a parallelogram. If you slice the parallelogram onto itself, you're going to get a plane figure. So you have half the circumference here, half the circumference here, and you have the radius. Remember, we cut through the radius. Essentially, this is what has appeared here, or this is what we have done, converting a circle all the way to a rectangle. And by doing this, I know that this is r, but what do I know as the circumference? The circumference is 2 pi r. So half of it will be half of 2 pi r. So it reduces to pi r. So the area of this rectangle, which represents this circle, is length, which is pi r, times the breadth, which is r. And that gives us pi r squared, because r is multiplying out 2. And this is why the area of a circle is pi r squared, because we converted the circle to a rectangle and then we're able to find the area of it. It's fascinating stuff. Three-dimensional figures, or 3D. We've been looking at 2D figures, but when it comes to three-dimensional figures, well, this is a cube. In fact, it's called the Rubik's Cube, and you can see that contains smaller cubes. Yes, so this is a cube. It's essentially like the father of a square. So it has squares on each side, 6 sides, 1, 2, 3, 4, 5, 6, and each face is a square, and that is what a cube is. But on the other hand, a cuboid, what we call the cuboid, is like the father of a rectangle. So let's look at this here. So this here, off the top, looks like a rectangle on the top, but it has the length, breadth, and then the height component. This also has length, breadth, and the height component. Now we have other things. This here, what does this look like? This is a cylinder, right? And this is a cylinder. Also has a circular cross section. When you cut it, this is the cross section. You can see that it's a circle. So it's like the father of a circle. Cylinder is essentially the father of a circle. A lot of circles stacked up together makes a cylinder. This is one of the ideas that we use to find a couple of things around a cylinder. Now what about this? This is a sphere, right? A sphere has a couple of interesting things around it. So a sphere is essentially like a family of circles, right? It starts from small circle, goes round, connected. A family of circles connected in a length, right? Family of circles connected through a length. Small, and it increases, and then goes all around and comes back to the same spot. So this is a sphere, and all of these can be investigated using the concept of pi. All of these can be investigated using the concept of pi. So you can find, and what we're interested in concerning these 3D figures is usually their volume. So you can find the volume of this, you can find the volume of this cuboid, you can find the volume of a cylinder, you can find the area of a cylinder. Realize that the cylinder has an area around it, and if the cylinder is covered, you can find the total surface area. This is the curved surface area. If this side is covered like a milk tin, we can find the area on the cross section. Meanwhile, it's even possible one side can be covered and the other side open. So all these are interesting facts that can come around the shape of a cylinder. Yes, so in relation to a circle or the sphere, when you cut a sphere up, you're going to get a circle. You're going to get a circle, cut it through its middle, you're going to equator, so to speak. You're going to get a circle as its cross section. And if you cut anywhere apart from the center, you're going to get a smaller circle. You cut anywhere apart from the center, but if you cut through the center, you get the greatest circle. So we need to remember that about spheres. Yes. So we'll look at how to calculate their volumes in another video, but for now, this is just introduction into the various 3D figures that we will be working with in mensuration. So we've looked at a few concepts in mensuration. Hope you enjoyed the video. Make sure you subscribe to support the channel, and also for those of you who love to get a cube, make sure that you go to the sponsors interview and drop your code, and we'll get you a cube in your school wherever you are. As long as you have about 20 or more learners in your school, we will get you your cubes.